The exam 3 that we were going to have today is in Brightspace. So just turn it in by midnight and I'll be happy. All right, so since nobody's in person, we're going to get started on chapter 9. This is our last section, last exam, number 4, and we'll cover.
I'm sorry, I don't mean to interrupt you. I was just curious. You said we can do our exam online and turn it in to you by midnight?
Yes.
Okay.
Have you done that before?
Yes.
Okay, good. If anybody hasn't, then well, there are I think there are instructions there. But if you have any trouble, just let me know and I'll walk you through it.
It's pretty easy.
Yeah, it's a PDF file, and you download it, fill it out, and then submit it in the same folder that you found it. Okay, chapter 9. Let's see. We got chapter 9 this week, and we got chapter 10 next week, followed by Le Chatelier's principle. Let me get that copied. So you'll know what you're looking for. Let's see here. Here it is. This is the lab we're going to be doing next week. Looks like that. And that's in Brightspace. It's kind of like that, the lab we did where we were, let's see, what is it called? Detecting signs of chemical change. There are a lot of little things that you do through the lab, so it's not boring. All right, and then today I was going to hand out, let's see, here's a review. There's the review document, that's in Brightspace. And I just completed, there's also a key in Brightspace. And I just completed the work problems for exam 4. And I had hard copies here. So maybe you can pick them up next week. And then chemical reactions, PowerPoints, you were going to get that today. And then next week we'll have chapter 10. All right, get that out of the way. All right, so I'm going to share the PowerPoints, which should be sitting over there waiting on me. So if you can't see that, let me know. Otherwise, we'll get rolling on chemical reactions. It seems like, I don't know, I get the feeling like we started off with basic principles in the beginning, the first couple of chapters. And then we kind of just jumped on the horse and rode off in every direction. And we keep coming back to certain topics. And you've had some exposure to chemical reactions already. So hopefully this will kind of pull things together rather than introduce a lot of new material. Okay, that's just an outline that's at the beginning of all my PowerPoint slide sets, but we don't need to stop there. Okay, just to beat a dead horse, a chemical reaction is a process in which at least two, well, not two, excuse me, reset, in which at least one new substance is produced as a result of the reaction. You could start off with just one substance and end up with a new substance. Or you could start off with one and end up with 2 or 3 or 4, like nitroglycerin, right? If you set off nitroglycerin, you get about 4 different gases. And it happens like that. which is why nitroglycerin is a good explosive. Or you can have 2 or more reactants, and you end up with several products, or you could combine those 2 into one. And we're going to define those in just a minute. In fact, the one I was just describing is a synthesis or a combination reaction. These are the thing about chemical reactions names, characterizing a chemical reaction as one type or another is a way of organizing our thoughts about the chemical reactions. It's not that chemical reactions have to strictly obey what we tell them, right? I've said before, and I'll say it again, nature just does what it does. And it's our job to try to make sense of it. And this is one of the ways we make sense of it, is naming types of reactions. So we've got the possibility for a combination reaction, which is also called a synthesis. And the other way around would be a decomposition, where you go from simple to multiple. Displacement. And we're going to have subsequent slides will characterize each one of these, which is also called a single replacement, or an exchange reaction called a double replacement. And then you've got oxidation reduction reactions. They can come in various forms. Combustion, anytime you burn something in oxygen, that's a combustion reaction. It's also an oxidation reduction reaction. A galvanic cell, which is also known as a battery. An electrolytic cell, which is a process used in plating metals. It's not the only place you use it, but that's one of them. Like, they don't have them anymore, but you might see them on classic automobiles. If you go to an automobile show, the chromed bumpers, they get chromed by a process of electrolysis. Okay, for the first type, a combination reaction or a synthesis. The concept here is you're taking 2 or more and making 1. So the X and the Y in this example are elements, and you're making a compound. That's one example. This is just an example. What you can also do is have 2 compounds, combine them into a single. So X and Y doesn't have to be elemental. Calcium plus sulfur yields calcium sulfide. That's an example. A synthesis or a combination. The other way around, you just flip the reaction around. So if you said, I'm going to use A and B. If you said A plus B yields C, then you can also go the other direction. And in that case, it would be a decomposition. So that reaction I referred to a few minutes ago, the nitroglycerin, is a rapid decomposition. It's an explosion. Goes from a simple to multiple components. The example they're giving here is copper 2 oxide yields copper plus oxygen. Now, we're not saying anything about these reactions with reference to whether or not they occur spontaneously or whether you have to drive them a certain direction. We're just saying this is what happens. The forces behind a reaction, we allude to them throughout the semester, and we say what are possible driving forces for reactions, and I think we got to that pretty early on in the semester. But to get into the nauseating detail of what drives chemical reactions, you're in the wrong course. You'll have to take I think it's second semester general chemistry. Then we get into the true driving forces for reactions. But for our purposes, we're just saying this is what happens, and this is what we call it. A single replacement or displacement, right, would be if you have something like that, and then mine's different than theirs. The C replaces one of these components. Let's say it replaces the A, like that. A good example is, this example is iron and copper sulfate yields copper and iron sulfate. Actually, I like, there's a better one. I like iron and aluminum oxide. Oh, excuse me. Sorry. I got it backwards. Rust plus aluminum. And that yields iron plus aluminum oxide. There we go. And my mind's gone blank. It'll come to me in a second. This is called thermite. If you've ever seen railroads, modern railroads under construction, when they want to join two rails, steel rails, they use thermite welding, right? And they probably have the area cordoned off so you can't get close to it, because this is an extremely violent reaction. And what it does is it produces this pure iron in the weld joint. And it's as if those former two rails now are a single rail. You grind it down and you can't tell where the rail lets off, where the one rail starts and the other one begins. But that's thermite. I like that reaction. You can find it on the internet, videos of that reaction, and it's pretty impressive. This is also an oxidation reduction reaction, but we haven't defined oxidation reduction, so just keep that in the back of your mind. All right, that was a single replacement. This replaces iron, or an exchange reaction. Excuse me, not an exchange. Displacement, excuse me. This was a displacement. Or a single replacement. Now you can also have situations where you have two compounds, and in the interest of simplicity, you just swap A with C, because remember the way we write these is cation, anion, cation, anion. So the cations would swap, or the anions would swap, whichever you prefer. And you would end up with a C and a B plus an A and a D. That's a double replacement. Or an exchange. These are fairly common reactions. This example here is silver nitrate in solution plus sodium chloride in solution yields silver chloride solid, which means it precipitates, drops out of solution when you put those two together. And what's left over is sodium nitrate. This also illustrates the point that double replacement reactions very often, very often, produce precipitates. In other words, solids as a consequence. And that can be viewed as one of the driving forces for the reaction, because if that solid drops out, say that was aqueous, and this was aqueous, and this is solid, and this is aqueous. If they're in solution, then what happens? If this solid forms, those two components, in this case silver and chlorine, are removed from the reaction mixture. And if you keep removing them, then these keep trying to react in order to replace it. Right? We're going to study that at the end of this chapter. It's called Le Chatelier's principle. All right, a combustion reaction. Anytime you combine something with oxygen, oxygen has to be one of the reactants. If oxygen is one of the reactants, and I mean oxygen in its most common stable form, O2, then you have a combustion reaction. This is also an oxidation reduction reaction, just like the this one. But combustion reactions are always oxidation reductions. And you know, single replacements are also, they're always oxidation reduction. And I'll explain why when we get to it. Okay, what type of reaction is this? Notice on the reactant side, there's just a single compound. And on the product side, you have several different products, several different substances. Right? This would be a decomposition. Decomposition going backwards like this. There you go. Now let's classify each one of these as either a combination, decomposition, displacement, exchange, or combustion. I think those are all the ones that we've covered so far. Okay. Look at the reactants first. In A, you have magnesium and hydrochloric acid. And you actually observed this reaction in one of the labs where you put acid on a strip of magnesium. And you saw what formed was hydrogen gas and kind of a whitish material to begin with. But gradually the magnesium disappeared. And it was converted into magnesium chloride with the evolution of the gas. Now, this is another driving force for reactions, is the formation of gases. And it's a similar concept to the one where you form a precipitate. If you form a gas, it's going to rise out of the solution and escape into the headspace. That effectively removes it from the reaction environment. And it forces the reaction to go even more toward products. For one reason, reactions can always be written in forward and reverse direction. And if you remove one of the components from this side, it can't go backwards. So it has to go forwards. Okay, so what kind is this? It's a single replacement reaction for this one, or a displacement. How about the next one? Hydrochloric acid and ammonia. Well, you got two compounds here, but they're combining to form a single compound. In fact, they're forming a solid, ammonium chloride. So this would be a synthesis reaction or a combination. Synthesis. This reaction is one that we used to use to test the airflow in our fume hoods. All you'd have to do is get a beaker of concentrated hydrochloric acid. Right? You can see the fumes coming off of it. And then another one with ammonia in it. And set them close to each other. The gases evaporate and combine above the beakers. And when they do that, they form a solid. It looks like a fog. It's a very finely divided solid, and it's light enough, each particle is light enough so that the airflow through the hood will drag it away. But it's not particularly hazardous. So you can see the movement of air in your fume hood. Let's see. Ammonia and oxygen produce nitrogen monoxide and water. The key here is oxygen. You see oxygen sitting right there combined with ammonia. That is a combustion reaction. And it's also an oxidation reduction reaction, which we haven't defined yet, but we will. In fact, we're going to do it right now. Oxidation reduction. The short version is redox. Now, why don't we say ox-red? Just doesn't sound right. Redox sounds better with the short version, and oxidation reduction sounds better with the long version. So take it or leave it. And the key to the reaction is electrons. During the reaction, electrons move from one atom to another one. Okay, and that's the terminology for that. Let me see. It's probably on a subsequent slide. Let's see. Let me look and see. Let's see here. I don't want to steal my own thunder. No, I guess I missed. Oh, it is down the road. It's on another slide, but I want to give it to you here. Oxidation reduction. Well, first of all, what is oxidation? Oxidation is anytime an atom loses an electron. So oxidation is a loss of electrons, whereas reduction is a gain of electrons. Now that can be one electron, it can be 2, 3, 4, 5, however many that is required for the reaction to proceed and be balanced. But oxidation is loss, reduction is gain. That's why if you have trouble remembering it, just remember this mnemonic. Oil rig. Oxidation is loss, reduction is gain. And you'll never forget it. And they always occur in pairs. You can't have oxidation in a chemical reaction. If something is oxidized, something else has to be reduced. Those electrons don't sit out there and accumulate to form an electrostatic charge. That's in physics. Chemistry, electrons have to go somewhere when they leave somewhere. So oxidation and reduction always occur together. So if something's oxidized, something else has to be reduced. Now, many reactions don't transfer electrons. They're non-redox reactions. Okay, so that the red lettering at the bottom gives you some clues as to whether or not the reaction is a redox reaction. If this clue doesn't work, it doesn't mean that the reaction is not redox. It just means that it doesn't satisfy the clue. And one of those clues is if you have a free element on one side of the reaction, either on the reactant side or the product side, and on the opposite side, reactants or products, that element is combined in a compound. that is a redox reaction. That's why I said that this reaction, oops, about to do it again. This thermite reaction is a redox reaction. Here you have an element, and over here on the product side, it's combined in a compound. Or you can look at it this way. There's a free element, but it used to be in a compound. Those are always redox reactions. Okay, in order to determine if you don't have this clue, and if you actually need to know how many electrons move, you got to know where we started with this one, where we ended up with that one. So if we're going from this iron to that iron, we've got to say what number or oxidation state is assigned to that element in this compound, and what oxidation state is assigned to the element here. And then compare them and say, okay, if it went from this number to that number, did it gain electrons or lose electrons? That's the idea behind defining the oxidation state or the oxidation number. And those numbers can be positive or negative. And for our purposes, they're always whole numbers. They're either positive or negative whole numbers. Now, it's easy to treat the oxidation state as a whole charge on the atom. Sometimes it is, but it doesn't have to be. You can use oxidation states for covalent compounds too. The calculation and the use of oxidation states is a bookkeeping scheme. It helps us track the movement of electrons. And there's some rules that go along with it, and I'll give them to you in just a minute. Rule number one, the oxidation number of an element in its most stable elemental state is 0. So this aluminum, which is a solid, is oxidation number 0, which means it's neutral, which stands to reason. This one also is neutral, and it has an oxidation number of 0. The oxidation number of a monatomic ion equals the charge on the ion. We don't have any ions here that are explicit, but if you had something like, I don't know, iron 3 plus, like that, then the oxidation number for that iron would be +3. It's equal to the charge. The oxidation numbers for alkali metals are always +1. Right? It's just like when we were trying to write compounds and name them, right? The first column, alkali metals, we consider them always +1. Well, in this schematic, in this scheme, this bookkeeping scheme, they're always +1 oxidation state. The ones next to them, the alkaline earths, are always +2. I don't have an example up here, but sodium in the compound sodium chloride, that oxidation number is +1 because it's an alkali metal. The oxidation number, we're going to stay on that side of the periodic table and go up to hydrogen. The oxidation number for hydrogen is +1 if the hydrogen comes first. So if we say HCl, that's a +1. If it comes second, if there's a metal first, like, let's see. Let me pick a good one. Oh, my mind's gone squirrely. How about this one? Like that. Magnesium hydride. These compounds exist. In this case, magnesium has to be a 2+ because it's an alkaline earth. So that means hydrogen has to be -1. Now, how do I know that? Well, that compound is neutral. So any accumulation of charge cannot exist. That has to be neutralized. Pluses have to be neutralized by minuses. So if this is a 2+ or +2, then 2 minus 2's come to 0. Okay. So in this case, hydrogen has to be a -1. But if it comes first, it's always +1. At this point, we're just going through the rules. This is how you tell what's what. And these rules give you a starting point, an anchor, so that you can determine the oxidation states of most elements in a compound. And then the ones that we don't have rules for, they can be calculated once you know, or once the rules tell you what the oxidation number is for the other elements. That's why we're doing this. Oops, there we go. Okay. If oxygen is in a compound, then it will have an oxidation number of -2, with one exception. So if we say, let's use magnesium again. Okay. That's +2. This is -2. Oh, excuse me. -2. But if oxygen is bound to itself and then bound to something else, like hydrogen peroxide, right? You find that in your bathroom on your medicine cabinet. It's a 3% solution of hydrogen peroxide. Okay. In that case, the hydrogens are +1. That means those two have to be -2, right? +1, +2, +1, +2. These together have to be -2 to balance the charge. That means each one of these oxygens has to be a -1. So anytime you have oxygen in a peroxide, each oxygen has an oxidation state of -1. Otherwise, if it's oxygen by itself in a compound, it's a -2. All right. When we're dealing with binary compounds and we're trying to decide how to assign the oxidation state, if you need a tiebreaker, then the more electronegative element is the one that's given the negative oxidation number in preference to the other one, which is the less electronegative. It's going to be more metallic-like. It'll have the positive oxidation number. That's just if you need to break a tie. For compounds, neutral compounds, oxidation numbers all have to add up to 0. Can't have any unbalanced charge. Now, if you do have a charge, and it doesn't say. I thought there should be another rule. Well, I'll just give it to you then. It's along the same lines. If you have a polyatomic ion, like PO4 3-, all of the oxidation numbers for these elements in that ion must add up to 3-. So if oxygen has to be a -2, then -2 times 8 is -8. And then we need to keep 3 of those minuses for this charge, right? So phosphorus only has to balance -5 with a +5. Okay, that means that the +5 and the -8 is a -3. Okay, so polyatomic ions are the most common types of arrangements where you'll need to use that rule. All right, next slide. Okay, here's some examples. We have 1, 2, 3, 4 compounds and 1 polyatomic ion. So this one, yep, that's correct. Potassium, right? What is this, a type 1, type 2, or type 3? Well, it's not a type 3 because you got a metal and a polyatomic ion. But the metal has a fixed charge because it is an alkali metal, right? So that means that its oxidation number has to be +1. We can do that one right now. Oxygen is -2 according to the rules, correct? So we can calculate chromium. It's like an algebraic expression that has one unknown. Here's our unknown. We can solve for it because we know the outcome has to be 0. All right, how many pluses do we have so far? Right, 2 pluses. How many minuses do we have so far? -14. Okay, so what charge does chromium have to balance against? Add these together. -12, correct? +2 and -14, -12. So this one together has to be a +12, right? To balance. That means each one of those chromium is a +6. And I think I got some animation here. There you go. That's how I got to those numbers. So what's the next one? CO3 2-. It's a polyatomic ion, obviously. Carbonate. Remember that one? Carbonate. All right. We know oxygen has to be a -2. Times 3 is a -6. Right? But we need to hold 2 of those minuses for the charge. So carbon only has to balance against -4, which means carbon is +4. Okay? And check yourself. Total on the oxygen is -6. And add a +4 gives you a 2- charge. Here we go. Let's say MnO2. What kind of compound is that? If we're going to name it, right? It's an oxide, a manganese oxide, but it's a type 2 compound. Manganese could have more than one possible charge. And when we first started naming compounds, type 1s, type 2s, type 3s, little did you realize that we were actually calculating oxidation numbers when we were trying to say what the manganese is. So we would write it like this. Manganese oxide. And then manganese has a variable charge. So oxygen's -2, -4 total, this +4. And that's the oxidation number on manganese, +4. How about PCl5? This is an example of a covalent compound, but we're going to use oxidation numbers as if there were charges. So PCl5 should be fairly simple. Right. Chlorine. Oh, I didn't give you that one. when you have to make a choice, this one's going to be the more electronegative, so it's going to be the negative number. And halogens, if they're combined with some other less electronegative element, they are given -1 oxidation number. So that's a -5. This has to be a +5. Fluorine is always -1. Chlorine and bromine and iodine, when they're combined with other elements, sometimes they vary. And in fact, if you look at a periodic table and you see the elements, then usually in the upper right-hand corner of the little box is maybe 1, 2, 3, 4, 5, maybe 6 or 7 different, looks like charges, minuses, pluses. Those are oxidation numbers that are possible for that element, depending on the compound in which it finds itself. And you'll find that when you look at fluorine on that type of periodic table, it's always -1, never anything else. But chlorine, bromine, iodine, they have different numbers. Some of them are positive. And if you have a compound where you have 2 halogens together, you need a tiebreaker. Right? So then we go back to that rule. If we have, say, bromine and iodine together, bromine and chlorine together, then chlorine is the more electronegative, so it's going to be the negative one. And we usually give it a -1, and bromine is whatever's left over, depending on the ratio of atoms in the compound. All right, and SF4. In this case, fluorine is -1. It's never anything else, right? So if fluorine's -1 and a total charge of -4, then sulfur has to be a +4 because there's only one of them. All right. Okay. Now, how do we use this information? Well, when we set up our equation, and it doesn't have to be balanced. It just, the compounds and the elements have to be written correctly first. Because sometimes we use redox math to balance an equation. Sometimes it's easier to manage the electrons first and then manage the atoms afterwards. And hopefully I'll be able to show you 1 or 2 of those. So you look for a change in oxidation number for any of the elements. And if you see a change in oxidation number, you know you have a redox reaction. Here's a good one. Calcium and chlorine makes calcium chloride. It's a very energetic reaction. And if you determine the oxidation numbers, calcium and chlorine are both elemental, so they have 0. But in the compound, remember the halogen is a -1, so that means 2 of them means there's -2 has to be balanced by a +2 for that 1 calcium. So what's the oxidation number for sulfur in H2SO4? There are 2 ways to approach this. If you're looking for the oxidation number for that element, you can do the whole compound, right? Like this, right? Hydrogen's first, so it's going to be a +1. So that's +2 total. Oxygen's -2, so it's a -8 total. Right? So that's a -6. Sulfur has to be a +6. Okay? But suppose you have this polyatomic ion right here. And it's in a different compound. Right? Is it going to have a different oxidation number for sulfur? Right? There's the polyatomic. So this one is -2 times 4 is a -8. Hold out two minuses for the charge. -6 plus 6. All right, so sulfur is going to be +6 whether you take the whole compound or you just take the polyatomic ion. It works either way. Okay. So there's some more terminology involved here. Let's use what if we use a combustion reaction? How about that? Methane plus oxygen yields carbon dioxide and water. Okay, that's gas 2. All right, so if we assign oxidation numbers to find out which one's which, this one's 0 because it's an element. In this case, hydrogen, even though it's second, it's still a +1. So that first rule I gave you, because carbon's not a metal. If this were a metal, then hydrogen would be a -1. But carbon's not a metal, so hydrogen is still +1. So that's +4 total. That means this carbon is a -4 oxidation number. Oxygen's -2, -4 total. That means this carbon is a +4. This one's a -2, and that's a +1. Okay, so what changed? We went from carbon -4 to carbon +4. It changed its oxidation number by how many units? Well, I like to go, if I start with a minus, how do I get to a 0? Well, to go from -4 to 0, you have to lose 4 electrons, right? And go from 0 to +4, you have to lose another 4 electrons, right? We're going positive, so that means the electrons have to go somewhere. This is oxidation. So going from here to here, we lose 8 electrons for each carbon, which is oxidation. Okay, since we have an oxidation, there has to be a reduction. So where's the reduction? Well, oxygen is an element here and a compound there and there. So in this case, the oxidation goes 2 directions. It goes from here to here. Let me get this out of the way. And it goes on down here like that. So this one goes from a 0 to a -2 here and here. So what does that mean? Right? That's a gain of 2 electrons for each oxygen. That's reduction. Okay? Now you can tell right off that it's not balanced because 2 electrons per oxygen, 8 electrons per carbon, right? The electrons must balance. Oxidation electrons have to be the same magnitude as reduction electrons. Right? Otherwise, you have an unbalanced charge, and that's electrostatics. And we don't do that in chemistry, usually. Okay, so oxidation and reduction have been defined. Okay, now, whatever is oxidized is a reducing agent. Right? So that's a reducing agent. And all you have to say is, if it is oxidized, it's a reducing agent because it provides electrons for the reduction of the other element. And if it's reduced, it's an oxidizing agent. Okay, that's an oxidizing agent. Okay. Oh, and there's your oil rig. Oxidation is loss, reduction is gain. This is just a summary reinforcing ideas, what oxidation and reduction are, what an agent is. An oxidizing agent is always reduced, and a reducing agent is always oxidized. They always occur together. And actually, we're beating the dead horse a little too much down there, but it's there for your entertainment. Now, your authors like to point out the fact that when oxidation occurs on an element, its oxidation number increases. It becomes more positive, and that stands to reason. If it's oxidized and losing negative charges with its electrons, then it has to become more positive. But it doesn't have to be a positive value. It just has to become more positive. So you could start at -7 on this scale and go to -4. It's becoming more positive, because in order to go from -7 to -4, you had to lose 3 electrons. And you can say the same, you have the same argument for reduction. The oxidation number has to become more negative for reduction. All righty. Let's see. We'll leave that stuff there. Oh, did somebody show up? Angela, no, somebody disappeared. Kelsey. Could be having internet problems. Okay, in this reaction, copper plus silver nitrate yields silver plus copper 2 nitrate. What's oxidized and what acts as the reducing agent? Okay, so if we have copper plus silver nitrate in solution, like that, and then it produces silver solid plus copper 2 nitrate. Then we want to know which species is being oxidized, which means which one is the reducing agent. So we assign oxidation numbers. Elements get zeros. Okay. Notice that the nitrate is the same on both sides, which means, based upon that argument I gave you for the sulfate polyatomic ion, this nitrate goes to that nitrate, which means nitrogen and oxygen in that polyatomic did not change. So we don't even have to look at those. They are unchanged oxidation states for both sides. Right. So we need to focus on the silver now. If this is a minus charge for the whole polyatomic ion, that means silver has to be +1. And the copper in this one, since this is -1, 2 minuses means copper is a +2. Okay, now we can say which one was oxidized. What is oxidized and acts as the reducing agent? So who loses electrons? Well, copper goes from 0 to +2, which is an increase in oxidation number, which means it was oxidized. So copper has a loss of 2 electrons per copper atom. That means it is the reducing agent. It provides electrons to reduce silver from +1 to 0. All right. That makes A the answer. Okay. Oh, another one. Which of the following are oxidation reduction reactions? And then identify the oxidizing agent and the reducing agent. All right. So A. We have zinc and hydrochloric acid. Yep. So far, so good. And that one. I think you guys did this one in that lab, the detecting signs. Okay. Now, is this an oxidation reduction reaction? For this one, you can use that trick. Zinc element in a compound here. This is an oxidation reduction reaction. But now what we want to do is identify the oxidizing agent and the reducing agent. So if it wants both of them, we might as well just assess the whole reaction. This one's 0, and this one's 0. Chlorine is a -1, +1 for hydrogen. This one's a -1, so zinc has to be a +2. Okay. So if zinc is going from 0 to +2, it's a loss. 2 electrons per zinc. That means zinc is oxidized. And that makes it the reducing agent. All right. And make a little more room up here. There we go. So that means, which one changes now? Hydrogen goes from +1 to 0. So it's a gain of 1 electron per hydrogen, which is reduced, which makes it the oxidizing agent. Okay. So that one is an oxidation reduction reaction. And zinc is the reducing agent. And HCl is the oxidizing agent. Even though chlorine doesn't change, we use whatever the compound is. We call it the oxidizing agent or the reducing agent. How about B? The dichromate ion plus hydroxide yields the chromate ion plus water. Is that an oxidation reduction reaction? And OH and 2 chromates and water. Well, let's see. This is -2, this is +1. So that gives you a -1 for the hydroxide. That's true. This one's -2, and this is +1. This is -2 for the oxygen, which is -14 total. Hold 2 negatives for the charge, which means we need to balance a -12 with a +12. That means this is a +6. 2 times +6 is +12. Okay, how about this side? Well, let's see, this is a -2, and that's a -8, hold 2 out, -6, +6. This is a non-redox reaction. B is a non-redox reaction. So it's not going to have a box around it. I'm going to erase these because I need some more room for the next one. Okay, copper 1 chloride. And that gives you copper 2 chloride plus copper metal. I left out the phases. I don't think we need them in this case. Okay, what changes? Well, the chloride's -1 on both sides. So chlorine doesn't change its oxidation number. But this copper is a +1, right, to balance that one. This one is a +2, and this one's a 0. Okay, so an interesting thing happens in this reaction. This is a decomposition reaction, right? This one becomes one reactant becomes 2 products, decomposition. Okay, so this, if we take, and notice there are 2 coppers here. So if we take one of the coppers and go to this one, what has happened? The oxidation number increases. That means it's oxidized. It's lost 1 electron per copper, which makes it oxidized, the reducing agent. The other copper can go down here. And that one gained 1 electron per copper, which makes it 0. It went from +1 to 0. That means this one is oxidized, this one is reduced. This is known as a disproportionation reaction. That's a mouthful. Copper chloride, in this case, acts as both the reducing agent and the oxidizing agent. Copper smelters, when they find their ore is composed primarily of copper 1 chloride, all they have to do is heat it up, grind it, make it a powder, and then heat it up, and it produces copper metal, which is what they're after, and copper 2 chloride. And then they take the copper 2 chloride and go through a different process and retrieve the copper from that one. But the first step, all you have to do is heat it up, and you get this reaction producing half of the moles then are extracted by this process as copper metal. Okay, now we've just been talking about what happens. We didn't actually state any laws, but now we're going to induce a theory called the collision theory that helps explain chemical reactions. Because this whole chapter is about chemical reactions, so we can go anywhere we want to try to understand the chemical reactions. The collision theory involves both molecular collisions. In other words, the atoms and molecules in a reaction mixture must collide. If they don't collide, they cannot react. There's no reaction if there's no collision. Okay? That's why they call it the collision theory. And when they collide, they must have a certain minimum amount of energy, because otherwise no reaction will occur. Very often you have to break bonds, and in order to break bonds, you've got to have enough energy for the collision to break a bond. Or if you're just bringing 2 elements together, maybe you just need enough energy to initiate the formation of a bond. Like, Well, calcium and chlorine gas, or calcium and oxygen, you would have to break an oxygen double bond before you could form the calcium oxygen bond. So that requires what we call activation energy. Some reactions require very little activation energy to get them started, like nitroglycerin. You just need a little bit of a push. You could take a bottle of nitroglycerin, pure nitroglycerin, drop it on the floor, and there wouldn't be anything left of this lab. It doesn't take much. And other reactions take a lot of activation energy, huge amounts to get them started. And parenthetically, the reactions that require just a little bit of activation energy are very fast, extremely fast reactions, explosions, in fact, some of them. And those that require a lot of activation energy are slow. But that's not the only thing that's required. You need, we've discussed, they have to collide. That's required. They have to have a certain minimum activation energy, and they have to be oriented properly. If the bonds that are going to form from this side of the molecule on that one and this side on that one, and they come together like this, nothing's going to happen. They have to orient properly in order for the proper bonds to form. You got to break some bonds and you have to form the bonds. So the orientation is critical. Those three things are required in the collision theory for a reaction to occur. And we've got individual slides for each one, so I'm not going to stop on them. I just leave them there long enough to see the black and white. Activation energy may be interpreted as kinetic energy. In other words, the molecules that are colliding have to be moving at a certain speed, depending on their mass, and gives them kinetic energy. Remember, kinetic energies can be determined for individual objects. ½ mv squared. And in chemistry, kinetic energy can be estimated, not estimated, I should say, a way of expressing kinetic energy is temperature. So the higher the temperature, the more kinetic energy the molecules have. So that's why when you increase the temperature, you usually get a faster reaction. And then the orientation in three-dimensional space. So if you've only got two reactants coming together, those are fairly easy to simulate, and they will happen. If you've got a reaction where 3 or more reactants have to come together, then the probability of having a reaction take place goes way down, because it's more difficult to get 3 to come in at exactly the right position, orientation to each other, that a reaction will occur. So those reactions are either rare, non-existent, or if they do happen, they're very slow. So this came out of your textbook. If you have proper orientation, then you find that you form the proper bond to go from NO to CO2 out of NO2 and CO. They're oriented properly to form that bond. These other orientations do not produce a reaction. Or at least they don't produce the desired reaction. I would qualify that statement if they come in and they orient improperly, but they have enough energy for an alternate reaction. often referred to as side reactions, then you may get the wrong product. And that very often happens. And that's when the chemist has to take, if he has no alternative, has to take the reaction mixture after the reaction has occurred and clean it up, separate the components, because he may be only after, he or she may only be after one of the products, and the other product is undesirable. Okay, what are the three factors necessary for a chemical reaction? Well, you need collisions, you need activation energy to be met, low activation is best, and proper orientation. Okay. Now, when this collision does occur and when you have a reaction, sometimes the reaction requires more energy. Okay, let me stick to this slide. Sometimes the reaction occurs a certain minimum amount of energy input, the activation energy. But if when the bonds form, you generally release energy. So if that release of energy exceeds the amount of energy you had to put in to get the reaction to go, then you have a surplus of energy, right? And the mixture should become warmer. In that case, you have an exothermic reaction. The example here is burning any kind of fuel. So those exothermic, and we can look at these in terms of system versus surroundings. I'm not sure if I showed you this before, but I'm going to now. If you have your system and your surroundings, and energy is transferred out of the system, that's exothermic. If energy is transferred in, that's endothermic. That's one way of looking at it. The other way is, say, if you have, if you're reacting and you say you get CB plus A, okay? If you put energy in here, energy in, and you get some energy out, the balance of energy is what determines exothermic and endothermic. If this one is greater than that one, then it's exothermic. If this one is greater than that one, then it's endothermic. And to the touch, it would feel cold. The reaction would cause you to sense cold on your hand. Okay, so before we get to that graph, let's look at it this way. For this example, say we've got a bond here, and we've got a bond here. See, C, B, A. We got to put energy in to break that bond. Okay, now you have A and B separate. Then B and C come together. And when that bond forms, energy comes out. Usually when a bond forms, well, we can interpret it that way. When a bond forms, you release energy because the product is more stable than the separate atoms. Now, when you look at it that way, if you put a little bit of energy to break the bond and you get a whole lot back when a new bond forms, that's exothermic. But if you have to put a lot of energy in to break the bond, but you only get a little bit back when a new bond forms, that's endothermic. There are a number of ways of interpreting. Okay, now let's look at the graph. The x-axis is reaction progress. as the reaction proceeds, and we're not saying what is actually happening, we're just saying the reaction proceeds from reactants to products. And then on the y-axis, we're identifying the amount of energy that's contained in the system, in the reactants on this side, and then on the products this side. So if you have total amount of energy identified here for the reactants, in order to get the reaction to occur, right, one of the factors is you got to put in some energy. So we have to raise the energy of the system here. So it goes up there, and this peak right here is the activation energy when it's compared to the starting energy, right? The reactants have this amount of energy, put some in, that's the activation energy. And then when we break those bonds by this activation energy and new bonds form, then the energy content of the products is lower than the energy content of the reactants. If that's the case, then this energy is released. This much energy from reactants to products is released. That is exothermic. Okay, so this is a graphical representation of an exothermic reaction. Now, what if we go backwards, right? Reactions can go backwards sometimes, very often actually. If we start with the products over here as the amount of energy of the reactants now, and you want to go backwards, what's the activation energy? The activation energy is huge. You go from here all the way up to there. That's the activation energy for the reverse reaction. And then you only get this little bit back. That means you had to put in a lot of energy and you only got a little bit back. That's endothermic. So an exothermic reaction in reverse is always endothermic. I think the next slide shows us, yeah, endothermic. Endothermic reactions, you put energy in and you get a little bit back maybe. Well, maybe that's the desired effect. If you put a lot of energy in, but you don't get much back, then where's that energy go? You can't create energy, you can't destroy energy. So the energy in effect is stored in the molecule, right? And in the case of photosynthesis in plants, what are they bringing together? They're bringing carbon dioxide from the atmosphere, water, and they're making compounds. Let's see. One of the first stable compounds is glucose. It's not the only one, but this is a possible overall reaction. That would be solid. So it takes energy in to break those bonds here. And then we only get a little bit of energy back maybe. So where'd the energy go? The energy is stored in the bonds of this molecule. That's why you can eat sugar and it gives you an energy boost because there's energy stored in the bonds. And what your body does as a heterotroph, that is a fancy word for animals, you're taking that molecule and you're going back the other direction. You're getting the energy out of it. So this way it's endothermic, and when you use it that way, it's exothermic. You get that energy back, plus that's why your body temperature is 98.6 and not room temperature, because you have some waste energy as a part of that reaction. And that's good, right? It's not bad. But that's physiology, and we don't have time to talk about that here. So Where does that energy come from? Here. For plants, for green plants, it's sunlight. The individual photons of light striking chlorophyll and some other molecules is captured to break those bonds and then stored in these molecules. Those plants are called autotrophs. And we are heterotrophs. Okay, so here's the endothermic reaction in reverse. The exothermic in reverse is endothermic. So the activation energy is very high, and we store energy in the products. So which one of these statements is correct? During an exothermic reaction, the average energy of the products is higher than the average energy of the reactants. No, it's the other way around. If the energy of the products is higher than the reactants, that's an endothermic reaction. You have stored energy in the products. So it's not A. In the endothermic reaction, the average energy of the products is lower than the average energy of the reactants. No, that's an exothermic reaction. So it has to be C, probably. Exothermic reaction, the average energy of the products is lower than that of the reactants. Yes. That's the true statement. Now, I mentioned earlier about reaction rates. A reaction rate is determined by, well, several things, actually. We can approach it from a theoretical standpoint. We can approach it from a practical standpoint. And I think we'll do the practical first. Definitions. The reaction rate is that rate of that reactants are consumed in a reaction, or you can identify it as the rate at which products are produced in a given time period for a chemical reaction. Usually, and we're not going to do it in this course, but if you have a desire to take second semester, you have to take first semester, and then second semester general chemistry, we get into a whole chapter on chemical kinetics, we call it, which is a study of reaction rates. And we usually study it in terms of the disappearance of a reactant. It's easier to manage it that way. And the calculations are easier that way too. But in this class, we're going to look at reaction rates in a practical sense. In other words, what can we do to speed up a reaction or slow it down, or what are the causes for those eventual determinations, fast or slow. Okay, one thing that you can do is identify the phases, the physical nature of the reactants. If a reactant, and remember, in a collision model, the reactants have to collide. So if this reactant is a big clump and this reactant's a big clump, what of the two reactants are going to interact? Only where they touch, right? So if you make them smaller and smaller and smaller, then you have more surface area, more area to touch for the collision. So if you reduce the size of the particles of the reactants, you get an increased reaction rate. All else being equal. If you increase the concentration of the reactants, say if they're all in the gas phase, and you make sure that the reactant concentration is increased, like their partial pressures are increased, or if they're in solution, you increase the concentration of the solutions, you have more opportunity for collisions, right? You increase the collision rate. That should increase the reaction rate as well. You increase the temperature. Now, where in those three factors does the temperature come in? Activation energy. Right? Increase the temperature, increase the kinetic energy of the reactants. Then when they collide, they have sufficient energy to react. More of them have sufficient energy. So this is the number of, this is the energy, excuse me. If this scale is the energy of the particles in a collection of reactants, and this is the number of the particles or molecules or atoms at that energy, then it typically goes like that. You have a lot of them are at this energy level here. Some of them don't have much. Some of them have a whole lot. So it's a spread. If you increase the temperature, right, then you get more of them at that energy level, right? And that means that there are more reactants with sufficient energy to meet the requirements of activation energy, and the reaction goes faster. And lastly, you can introduce a catalyst. So what does a catalyst do? Well, remember that diagram. This is reaction progress. And this is the energy of the reactants or the products. And if we start off here, about there, and then we put enough energy in for the reaction to go, and then it goes down here. So this is the reactants. This is the products. Right? And that is an exothermic reaction. This is the activation energy from here to here. That's for a reaction where no catalyst is introduced. If you introduced a catalyst, and a catalyst is specifically designed to increase the reaction rate, but the catalyst is not consumed. In other words, it participates in the reaction, but the catalyst comes in on this side and comes out on that side, apparently unchanged. But what does it do? How does it speed up the reaction? The catalyst goes and reduces the activation energy. So the activation energy here with a catalyst, okay? Reduce the activation energy. That means at a given temperature, now you have more reactants with sufficient energy to meet that obstacle and get over it. That's what catalysts do. Okay, so the physical nature of the reactants includes the physical state, solid, liquid, or gas, and the particle size. When the reactants are all the same physical state, they're all solids, all liquids, or all gases, or they're all in solution, then the reaction rate is generally faster between the liquid state reactants than between the solid state reactants. And the fastest reaction rates occur for gaseous state reactants. That's simply because, well, actually two things. You want as much opportunity for the reactants to collide as possible. If they're in the solid state, that's difficult, unless the particle sizes are really small. In the liquid state, now they have more opportunity to interact. But in the gaseous state, they can intermingle, right? Remember, two gases always form a solution. They can intermingle. Plus, there's one other thing. The kinetic energy. Remember, we studied disruptive forces. The kinetic energy of liquids a liquid is greater than a solid, and the kinetic energy of the gas is greater than a liquid. So the gases they have an advantage from the beginning because they have more kinetic energy for the molecules. Now, when you, if you have any relatives that are working the coal mines, you'll know that one of the dangers is mine explosions. And those can happen one of two ways, generally. If you dig into a seam of coal that has trapped in it lots of methane, then there's that gas, and it easily mixes with the other gases that you're breathing, which have oxygen in them, and all they need is a spark to set them off. And those reactions occur very fast. The other type is coal dust, right? The material in the coal has a lot of energy stored in it, and if you mix it with oxygen and the particle size is really large, then that piece of coal will burn slowly. But if they're very small particle size, it has lots of surface area to react with the oxygen gas, then all you need is a spark, and that can set off an explosion too. That's why mine safety engineers are very particular about moving lots of air through a mine to clear out the dust that's produced. You got to get that dust out of there so it doesn't accumulate to the point where it can become a hazard, both for breathing and for explosions, actually. Okay. Right, we talked about this, coal mine dust explosions. Yeah, that's a real hazard. Concentrations, there are more molecules of that reactant present in the reaction mixture, thus there are more collisions. Right, so more collisions means more probability of reaction, which means increased reaction rate. Temperature, temperature just means that the reactants have sufficient energy to overcome the activation energy. And the presence of a catalyst simply provides an alternate reaction pathway for the reaction to proceed. That means that the catalyst is a participant in the reaction, but only as long as it takes for the reaction to occur, and then it separates and it goes find another reactant to help. We have inorganic and organic or biological catalysts. Biological catalysts are called enzymes. Now, enzymes in your body, yes, they are catalysts. They do participate in the reaction, and then they withdraw from the reaction and are ready to catalyze another reaction. But enzymes are special. They don't just make a reaction go faster. They actually control the reaction. Whether the reaction occurs, what conditions are required for it to occur, and usually, not always, but usually, an enzyme will only catalyze the forward reaction. If you need a reverse reaction, you need a new enzyme. Now, there are some exceptions and some very important ones, but and for the largest part, enzymes are particular for a forward reaction. And you'll have to take biochemistry to get that one. To get some plausible explanations for why that happens. Okay, here's the picture that I just drew you. Notice that the catalyzed activation energy is reduced. And the short answer is it's reduced because it provides another pathway that requires less energy. Okay, what's the function of a catalyst in the chemical reaction? Increase the rate of the reaction by decreasing the activation energy. That's the simplest explanation right there in one sentence. Now that we know something about reaction rates, we're going to talk about equilibrium. These are two important concepts that are somewhat complementary. In other words, when I introduced the concept of equilibrium to my second semester general chemistry class, we go through kinetics first, because in order to understand equilibrium, you need to have an understanding of kinetics. And we've done that in this class right now. We've talked about reaction rates. Right? Equilibrium is a condition in a chemical reaction. Actually, equilibrium can be used for various things, different types of equilibrium. We're talking about chemical equilibrium. And chemical equilibrium is, for this hypothetical reaction, occurs macroscopically. What you witness with your eyes and measurements is when the concentrations of the reactions and products do not change. Right? So the macroscopic world says no change in concentrations. Okay? But on the microscopic world, what's happening where we can't see it is that the rates, the reactions are still occurring. Even though we don't see a change in concentrations, we're seeing a rate, the forward rate and the reverse rate. The forward rate is occurring at a certain rate when we reach equilibrium, and the reverse reaction is occurring at exactly the same rate. That's why we don't see a change, because we're forming these as fast as they're disappearing, or we're using these as fast as they're reappearing. So in the macroscopic world, we don't see a change. But on the microscopic world, the activity is furious, very fast. Things are happening that you couldn't keep track of if you were small enough to see it. So it all has to do with reaction rates. The forward rate and the reverse rate are equal. That's what occurs at chemical equilibrium. Now, for every reaction, this occurs under different conditions, and concentrations of products are not always the same for every reaction relative to the reactants. These are unique for each reaction. So we need a way to express that, and I'm going to show you in just a second. This is one way of looking at it. For this reaction where hydrogen gas and iodine are combined to make hydrogen iodide, in the forward reaction, the reverse reaction is hydrogen iodide decomposes into hydrogen and iodine, right? And the reaction rates in the beginning, if we're starting off with hydrogen and iodine as our reactants, in the beginning, the forward rate is all there is. Notice down here, the reaction rate, the reverse reaction rate is 0, because there are no products to react and return to the reactant side. But gradually, you start building up products, and they react to return to the reactant side, and eventually they stabilize at a given rate, one forward and one reverse, equal rates. Now, some reactions take a very short time to reach this point of equilibrium, and some take a very long time to reach that condition. This is another way of looking at it. If you look at the concentration of the products versus the reactants, you find that when you first start, the reactants here on this purple line, they start off at a certain amount, concentrations, and there are no products. So over time, the products gradually build up and the reactants are gradually consumed until you reach a point where they appear to be stable, no change. Okay, that brings up the idea of reversible reactions. Essentially, all reactions are reversible. They can go in either direction on the microscopic level. Some of them, actually, it's a matter of timing. Over very short periods of time, we can say that all reactions are reversible. Over longer periods of time, that tends to be problematic. In other words, the reaction may go to a certain point where essentially all of the reactants are consumed into products. But for our purposes, on the microscopic level, we can say that all reactions are reversible. But the reverse rate may be very slow. And if it's slow enough, then it may appear that all of the reactants have disappeared and you have now products only. And that would be called an irreversible reaction. Okay. A state of chemical equilibrium is reached when the concentrations of all reactants and all products remain constant. And a reversible reaction is one in which the conversion of reactants to products and the conversion of products to reactants occur simultaneously. All right. So now we're going to, just a second, let me check my hard copy. Yes. Okay. Where we're going to end this discussion, 9. Yeah, we're close to the end. We've got 9 sections in this chapter, so it'd be 9.9 when we get to the end. So what we need to do now is look at the equilibrium reaction that's at equilibrium. And this vessel is in a closed container, and obviously, right, all the reactants and all the products are gases. If it's not in an enclosed container, those gases will just blow out and you've got no reaction. So they have to be in a closed container. What happens, do you think, if this reaction is at equilibrium? Ooh, CO2. Those are all gases. What happens at equilibrium? Now the reaction rates are equal. You have some reactants left, you have some products left, and they're going backwards and forwards, same rates. What happens if we add more water to the flask? More here, right? We increase that amount. What happens? On the microscopic level, now you've got more water molecules in there. You've increased the concentration of this reactant. And if there are any carbon monoxide molecules there, they will encounter water more frequently. Okay, you've upset the apple cart, as they say. It was happy before, equilibrium. Now we've introduced more water. So what's going to happen? Well, you're going to get more reactions between carbon monoxide and water. That produces more product. So now the shift is going to be, you're going to increase the forward rate while the return rate is trying to adjust also. Only when these two return to an equality are you equilibrium again. So the way we say this is, if you add a reactant, you shift the reaction to the right, or products. In another situation, suppose instead we're now at equilibrium again, and we're going to add some hydrogen. Now you've got more collisions on this side, and it drives it back to the left for the same reasons. You have more frequent collisions, more reactions can occur. The rate of the reverse reaction now increases until you've got enough on this side of reactants to give you an equal, a balancing forward reaction to the reverse. Now equilibrium will be reestablished, but it shifts to the left for the purposes of calculating concentration. Okay. Now, there's a way to express that when equilibrium occurs. And the next slide should give us, there we go. I need to change that slide. I don't like that slide. And I'll show you why. This is often referred to as the law of mass action. And it allows you to calculate an equilibrium constant at a fixed temperature. If you change the temperature, then you will change the constant. But it will be constant for any given reaction if the temperature is maintained at a certain value and not changed. Okay, so our reaction, I'm going to write the reaction a little differently than that. I don't like the W, X, Y's, and Z's in there. So I write it like this. Little a is the coefficient for this reactant. Little b is the coefficient for that reactant. And we get products like that. So the little letters are the coefficients, and the big letters are the substances. Now, we need a way of expressing concentration. Very commonly, the concentration is expressed as in molarity, moles per liter, even for gases. And the convention is, if we're going to express concentration, we put a square bracket around it to indicate molarity. So the equilibrium constant is expressed by the concentration of the C, or one of the products, raised to the coefficient of the balanced equation. And then multiply that times any other products you have, raised to their respective coefficient powers. Okay, that's in the numerator. The denominator then is this. There we go. Now, that is a constant. As long as the temperature doesn't change, that value will be constant, and it doesn't matter what the concentrations are. All it matters is, at equilibrium, what are the concentrations? And for any given chemical reaction at a fixed temperature, this is indeed a constant value. Now, the other possibility we have, let me check my hard copy again to see if we're going to cover this. No, it's not in a slide. So what I'm going to do is say, this is in molarity. Sometimes if all the reactants are gaseous, sometimes it's more convenient to use partial pressures. So a different way of expressing this one in gaseous phase is to say, if they're all gases, then we would say the partial pressure of C to the C power times the partial pressure of D to the D power, just like that, of A to the A power times that one, B to the B power. Now, these two values are not the same. Using molarity gives you one constant. Using partial pressures gives you a different constant. So you need to know how they were derived in order to use either one of those. And if you look up these constant values, equilibrium constants, in a reference manual, the tables will tell you, somewhere in that table will tell you the origin. Is it from molarity? Is it from partial pressures? Whatever the concentrations happen to be. Okay. Let's see, how are we doing on time? 11? Oh, okay. Yeah, we're good. So I don't have to rush. All right, so that's an expression of equilibrium. So if you if we increase, let's see, our first scenario where we added some reactant over here, then that would be down here. That would increase the denominator and temporarily decrease the value, right? So in order to make it back to this value, in order to reestablish the constant, then some of this has to disappear and some of this has to reappear. And some of this will disappear too because it's reacting. So once those numbers have stabilized again, they may be different values, but the expression will give you the exact same constant once they reestablish equilibrium. Okay, I said that already. Molar concentrations are square brackets. Products are always in the numerator, reactants are always in the denominator, and the coefficients of the balanced equation are powers of those concentrations. Now, K can have various subscripts. In general, EQ is what we use for equilibrium. But sometimes we have subscripts that are specially assigned to different types of reactions. And I'm not going to say any more about that. Just be aware that you can have a different subscript for an equilibrium expression depending on the origin of the reaction. Now, here's another thing about equilibrium constants. The only values that enter this expression are either gas or solution concentrations. If any one of these reactants is a solid or a pure liquid, not a solution, but a pure liquid, then they are not put in the expression. You just ignore them. Primarily because during the reaction, their concentrations don't change, right? A pure liquid just gets smaller, but the concentration is still the same as it always has been. Solids are the same. They may get smaller, they may get larger, but their concentration expression is essentially unity, just one. So we don't put them in the expression of equilibrium. Now that doesn't mean they don't participate, they do. But as far as equilibrium is concerned, they don't exist. Another way to think of it is the effect of the solids and liquids are buried in the constant here. Whatever makes sense to you, that it doesn't matter. Just remember, pure liquids and solids are excluded from the expression. So how does the equilibrium constant change with a temperature change? Okay, here's the best way to look at that, I think. Let's leave that much. Yeah. Okay, I was just thinking for a second. In the first scenario, delta H means heat. It's a special term called enthalpy, but for our purposes, just think of it as heat. You can put, if it's an exothermic reaction, then we're going to have heat as a product. In other words, it's going to get warmer. You're going to feel that heat coming out of the reaction. Where was that heat before? Well, that energy was over here in the reactants. Now it's separate. That's an exothermic reaction. Okay, so if we think of this heat as a term in our equilibrium, if we add heat to this reaction, then think of it as a product. Then if we increase this value, it's going to force the reaction back that direction, which does what? It decreases these and increases these. So if you increase the temperature for an exothermic reaction, and you increase the temperature, then you're going to drive the reaction back this way, decrease that, increase that, the K, EQ, decreases. Okay? And if you decrease the temperature, then you get the opposite effect. You will increase the KEQ. If you decrease the temperature, you're reducing this part, this term, which pulls the reaction this way. Increase that, decrease this, increases the K. So what happens if it's an endothermic reaction? In that case, we put the heat term on this side. And this is endothermic. So for an endothermic reaction, we're putting heat in and it's being stored over here in these bonds. So if you increase the temperature, what happens? You're adding this term, which means you're making less of this and more of that. So this is increasing, this is decreasing. So in the endothermic case, if you increase the temperature, the equilibrium constant increases. Okay? And if you decrease the temperature, then the K will decrease. Okay? Another way to look at it, we're trying to extract information from a balanced equation and the K that goes with it. In this case, and in this slide, what we're saying is that what if the K value is very large, much, much greater than 1? If it's very large, what does that mean? That means there's lots of product, right, and very little reactant. You decrease the denominator, increase the numerator. That means the reaction favors the product side, heavily favors the product side at equilibrium. If the KEQ is very small, just the opposite. Very small means the numerator is small, not much product. And denominator, the reactants are still there. Lots of reactants are still there. That's if the KEQ is small. Now, at this point, I want to draw a distinction between equilibrium constant and equilibrium position. We've alluded to it before, but I'm gonna hammer on it right now. Remember when we added something in here and saw the shift? The equilibrium constant is constant. I mean, that's what it is. It's a constant as long as the temperature is the same. But when we add something in one side, or we take it away, or whatever we do to it, if we change the concentration, the equilibrium will be reestablished, but the equilibrium position will be different. Say if we add more A, some of it's going to be changed over here, but it won't use all of it. It'll decrease some B, it'll decrease A, but not all of it, leave some behind. So A will increase, C and D will both increase. Now we get the same constant, but we've got a different position. We've got different concentrations. That's a different equilibrium position. That's an important distinction between the two. The equilibrium, actually, the equilibrium position well, it's stable eventually once it reaches equilibrium, but the position itself is not a constant. The concentrations will change. Okay, so this table comes straight out of your textbook, and it just refers to what can we derive? What information can we derive from the K? I mentioned earlier, if it's very large, we're favoring products. If it's very small, we're favoring reactants. If it's in between somewhere, then you're roughly equal. You're not favoring either side. And some textbooks say if K is equal to 1, then you're not favoring either side. But notice that here you got these powers, so you can't say that. You could have you could have equal amounts of C and D to A and B, but their KEQ would not be 1 because they might have different coefficients, right? So that's why we say it's kind of murky in the middle. All right, so here's an expression. Assume that there are no solids and no pure liquids in this reaction. We have hydrogen iodine and hydrogen iodide as the product. In that reaction, as given, H2 plus I2 yields 2HI. What would be the expression for that? Well, we need, in the numerator, we need HI because it's a product. And we also need the coefficient as the power. And then the reactants are this and this, right? And the coefficient is 1 for each one of those, so it's the power of 1. So that would be the equilibrium expression for this reaction, right there. Now, we've been dancing around Le Chatelier's principle now for the past 6 or 7 or 8 slides. But this is a black and white statement of Le Chatelier's principle. And Le Chatelier was a Frenchman, so this is the English version. If you have a system at equilibrium, and we're talking about a chemical system, and it's stable, with stable concentrations of reactants and products, and you do anything that disturbs it, that applies a stress to the system. Some things you do to it are not stressful, and I'll explain that in just a minute. But if you do something to the equilibrium system that does apply a stress to it, then it will respond. The system will respond so as to mitigate the stress, reduce the effect of the stress. Now, at this point, we've only talked about concentrations, like if we add something or take something away. That's one way to stress a system. And before we leave this slide, I'd like to make a point. Remember this for next week's lab. When the question arises in your lab and you need to report whether the reaction moves to one side or the other, if you say that the stress shifts the reaction to the right, then that doesn't mean anything unless you're referencing a balanced equation. If you have an equation there in your answer and you say, now it shifts to the right or it shifts to the left, that means something. But if you just simply scribble in there, shift to the right, shift to the left, without referencing a reaction, a balanced equation, then it means nothing. Because who knows, you could flip the equation around and then your answer would be wrong. Now, if the question itself references an equation and you say shifts left or right, then that's a valid answer because you have that reference equation. But if you're saying something about the system and you don't have a balanced equation to refer to, then your answer cannot be right, because right or left doesn't have any meaning. Okay, what kind of stresses can we impose upon an equilibrium system? We've already talked about concentration changes. So if you change the concentration of any of the reactants or the products, then the system will respond. Say if we increase C, the shift will be toward A and B. If we decrease C, the shift will be towards C and D, trying to replace some of that C. So concentration effects are fairly easy to come by. And that's another reason that solids and liquids aren't considered, right? Because if you have a solid in your reaction mixture and you throw more solid into it, you haven't changed the solid concentration at all. You put more solid there, but the concentration is still. You've changed the capacity factor or the extrinsic factor, but you haven't changed an intrinsic factor, which is concentration. Okay. All right. And when the system responds, the equilibrium position will change. The equilibrium constant will not change, but the position will change. And that's what those statements mean. This is came straight out of your textbook, and it just shows what happens. The position changes. Notice at equilibrium, after you've increased one and it reestablishes equilibrium, you've got a different mix of these concentrations on this side than you did there. But you still got the same reaction. You still got the same equilibrium constant. And you put those concentrations into the expression and they will pop out with the same constant. But the position has changed. Notice you've got less nitrogen now, more hydrogen, and more ammonia. Okay, we talked about temperature. What effect does temperature have on the situation? And the scenario where we put heat as a reactant or a product, if it's endothermic, it goes on the reactant side. If it's exothermic, it goes on the product side. Then when you change the temperature, you can say something about its effect, its Le Chatelier effect on the equilibrium, right? If you add heat here, it's going to shift to the right. If the heat term is on this side and you add heat, it shifts to the left. Sometimes you can see that change in color, right? For this reaction, the cobalt chloride 4 2- ion reacts with water and forms what we call a complex ion, cobalt and 6 waters with chloride extra. Well, the reactant on the left, the cobalt chloride on the left, that ion produces a blue color. But when we, and notice they've got a heat term here. This is an exothermic reaction. So if it's blue and then we cool it down, then we're removing heat. We're removing this term and causing the reaction to shift toward the product, which is pink. That's why when we ice this solution down, it turns pink. because we're producing more of this complex ion. So you can actually see the effect in that case. Okay, how about pressure? When would pressure change affect chemical equilibrium? Well, first condition is pressure on a solution will have no effect. But pressure where the gases are reactants might have an effect. It depends on how the pressure was changed. And usually when you change pressure for a reaction system, it's in an enclosed vessel, right? So the reaction, the system is inside the vessel. And the only way to change pressure is to move that piston. So if you decrease the volume, the pressure goes up. And if you increase the volume, pressure goes down. Now, how do we tell what effect there is? Well, the key is in the moles of gas on the reactant side versus the moles of the gas on the product side. And here's our example right here. Nitrogen gas plus hydrogen gas yields ammonia. And that's an exothermic reaction. So, and the change in pressure doesn't have any effect on it. It's not influencing this delta H at all. That's just there for discussion, and we may use it in a minute. But notice that the reactants have 1 mole of nitrogen and 3 moles of hydrogen. That's the ratio. So we have 4 moles of gas on the reactant side, 2 moles of gas on the product side. If you increase the pressure by decreasing the volume, you're providing less space for the reactants, 4 moles of reactants. So the system responds by reducing the number of moles of gas. And the only way it can do that is to react these nitrogen and hydrogen molecules and make ammonia, because you're going from 4 to 2. So when you increase the pressure by decreasing the volume, you put these reactants in closer proximity to each other, so the reactions are more likely to occur, and we produce product. So, and if we decrease the pressure by increasing the volume, now you're favoring more moles of gas can fill that space, and the reaction is favored in the reactant side because it has more moles of gas. Okay, that is a valid stress. That stresses the system by changing the volume and consequently the pressure. If we change the pressure by adding an inert gas, something that will not react with any of the reactants or products, the effect is 0. Nothing happens. I would submit also, if you add a gas in there that's not part of the reaction itself, say if we add, well, actually, if you add a different gas, like say oxygen to that mixture, it's going to react with either the reactants or products, and then you don't have the same reaction. So that's not a good argument. Inert gas is the best way to express this. If you put an inert gas in there, you increase the pressure, but you don't change the equilibrium at all. How about a catalyst? If we add a catalyst, what does it do? It simply speeds up the reaction in both directions, right? So it doesn't shift the equilibrium at all. It just means that the equilibrium is reached more quickly. It does not change the position. Okay, what factors affect the equilibrium of a reaction according to Le Chatelier? Well, concentration, temperature, and pressure. Pressure is, well, temperature is also dependent upon whether the reaction is endothermic or exothermic. Some rare reactions are neither. They're like isothermic. In other words, they don't give off energy, they don't consume energy. In that case, temperature change would have no effect on the equilibrium. Pressure depends on the gases. Right? If you have gas, say if you have gas on one side and no gas on the other side, then increasing the pressure will cause the gas to go toward the side that doesn't have any gas. All right. Oh, we're down to concept question. Okay. So now we're close to the end. Let me see. I'm covering up a little bit on my side. There we go. All right. A breathalyzer. I've never breathed into one of those. Never had the opportunity to be caught drunk driving. A breathalyzer is used to determine the level of ethanol in the body of a suspected intoxicated driver. And it uses the chemical reaction given below. It takes the ethanol that actually, once you drink ethanol, it goes into your bloodstream, and some of it comes out in your lungs, right, in your breath. That's what they're looking for. And when they measure the amount of ethanol in your breath, that can be correlated with the amount that's actually in your system, in your blood alcohol level. So the reaction takes potassium dichromate, ethanol, and sulfuric acid. And that reaction produces chromium 3 sulfate, potassium sulfate, and CH3COOH. That's another way of writing acetic acid. C2H3O2. See, C2, oops, H4. I should write it this way. H. There's your acidic hydrogen. And we haven't talked about acids yet, but we will next chapter. H, C2H3O2. They're the same molecule. And water. And it produces a reddish orange to green color in the presence of ethanol. The color is probably due to this chromate right here. Right? This is a redox reaction. Remember, we determined the oxidation number for chromium in this molecule is +6. The oxidation number of this chromium is +3. So the chromium has been reduced, and the effect of that is to change its color in the presence of water. So in this reaction, something is undergoing reduction. Chromium is undergoing reduction. Chromium 6+ is undergoing reduction to chromium 3+, while carbon, I think this carbon here, is undergoing oxidation. Oh, there are possible answers. Okay. So 6+ to 3+, so it's got to be C or D. And then ethanol is undergoing oxidation, so that's true. While ethanol is undergoing oxidation too. That's true. Both of these are true. So it's still C or D. And blank is the oxidizing agent. So what's the oxidizing agent? It's the one that's reduced. So K2C2CR2O7 is the one that is reduced, so it's the oxidizing agent. So C should be the answer. Oh, I see the animation is telling us, okay, we're going to calculate the oxidation numbers first. And then we're going to say, those are the answers. There you go. Now, calculating the oxidation number for carbon is somewhat problematic. So I don't intend to give you any that have these lots of carbons in them that where you have to work the oxidation number. If you get a carbon, it's probably either going to be something like methane or carbon dioxide, where you can do it. It's a really simple calculation. This example would be problematic. And we have to introduce some other controlling rules in order to get it there. But it's still a valid calculation. And that's it. So we're done with time to spare.